So recall, we were doing Euclidean field theory, XU and gauge field theory. With gauge action as 1 by 4 d4x f mu nu a f mu nu a. And we did calculations in background gauge, which means we expanded the gauge field A mu about a background A mu bar plus there's a 4g square here. G0 small a mu a. And then when we calculated the partition function, which was the S calculated for the background, S gauge calculated for the background, and the functional integral over these fluctuations, small fluctuations, and the Faddeev-Popov gauss of action, which was interaction action expanded up to quadratic in field small a, and some gauge fixing and a corresponding Faddeev-Popov. This is what we did. And the gauge fixing action we chose to be half d4x covariant derivative of a mu, covariant derivative in background a capital bar a d nu a nu a, where covariant derivative a nu bar of a was d mu of a nu a plus FABC AB mu small a nu c. And the Faddeev-Popov action was d4x d mu bar of c bar a d mu c bar of a. And when with this calculation, what we discovered was that this partition function could be written as exponential minus in the momentum space d4q by 2 pi 4 1 by 4 g square of q f mu nu bar minus q, tilde was the Fourier transform of f, times f mu nu bar to say that it was in the field strength for the background gauge, and tilde is the Fourier transform, where 1 by g square q was 1 by g0 square minus 1 minus 12 CV by 48 pi square log q square. And CV for SU n gauge theories is equal to n. The quadratic Casimir for the adjoint representation. V stands for vector representation or adjoint representation. This equation I could alternately write as 1 by g square of q prime is 1 by g square of q minus, this is 11, so plus CV 48 pi square log q prime square by q square. So that's how the coupling constants at two different momenta are related to each other. I could rewrite this equation by inverting it as g square of q prime is g square of q divided by 1 plus 11 CV 48 pi square log q square. Something is missing. I have missed a g squared somewhere here. Is that right? If I invert this, that's right, huh? And this tells me that g square of q prime is smaller than g square of q if q prime square is greater than q square. So that means coupling constant reduces as we increase momentum. So that's the special property of this theory. And we introduce a concept called beta function, beta of g, which is twice derivative of g of q square with respect to derivative of log q square. And this object is minus 11 g square of q square times CV by 48 pi square and is negative. So this important property of non-abelian gauge theories is that the beta function is negative. This is what we did last time. And then we said we'll add matter to it. Add matter to this theory, which means take action, which was the action, the gauge action, plus an action for a set of scalar fields, plus an action for a set of fermion fields. For a Dirac fermion in some representation Rf of SUN. Rf could be n-dimensional representation or the adjoint representation, which is n square minus 1 dimensional, given in terms of matrices n square times 1 minus 1 times n square minus 1, or n-dimensional representation where the charges for such a fermions, the SUN charges, are given by n cross n matrices. And for that we wrote the action SF is d4x psi bar I. I is the index, SUN index corresponding to whatever representation this fermion is in, times d slash ij psi j, where d mu ij is delta mu delta ij minus I a mu T a I j R f. So this is this covariant derivative for the representation Rf, which is given, whose components are labeled by these ij's, and T a I j is the corresponding matrix. So T a I j is n cross n for the defining representation, n-dimensional defining representation. It is n square minus 1 cross n square minus 1 for adjoint representation, each T a. And then for a complex scalar in some representation R s of SUN, S scalar is d4x d mu phi dagger L d mu phi L. where d mu phi L is d mu phi L minus I A mu A T A L M of R S phi M. Last time I think I had put in factor half. Some of you have already corrected it, that for complex fields you don't need to put, because Feynman rules I wrote later were for complex fields. And then we wrote Feynman rules for it. And we did, the exercise to be done was that you do the calculations now for this full theory of gauge fields and scalar and fermion matter, and find out what is the contribution that would come from beta function of the gauge theory due to these fermions and scalars. That is what we wanted to do is a calculation for that theory in the background gauge, which means expand again as A mu background plus G0 small a, and do integrations over A mu A and psi I and phi I, pi L, which means we want to calculate functional integral dA, d phi star, d psi bar, d psi, dc of exponential minus s interaction of the full action. This is a gauge field A. This is the full A. Psi and phi and SG and A. That's the full one, right? Somewhere I wrote 3 S's. Here, SG S. This is the full S.
You're not writing the corresponding background field for.
Yeah, no. Yeah. I see. No, the fermions. Last time I tried to remember, if you argue, is that this object was 1 by g square. So this object, whereas these objects don't have any g square. So these are one order smaller in couplings as compared to SG. SG means the SG bar. But the quadratic piece that is in SG that depends on small a's is of the same order in G as psi and phi. So you calculate in the background of the gauge field, take small a and phi and psi all as perturbation. That's clear? So we had an which is S interaction, which is quadratic in fluctuation fields, which means A, phi and phi star, psi and psi star, minus gauge fixing minus Fadi Popov. This is what we want to integrate. The gauge fixing action is the same, Fadi Popov is the same. So you take only quadratic part in the full S, quadratic in A's, which means there's 2 A's, 2 phi's, 2 psi's, or mixed ones, A and small a and a phi, small a and a psi. So keep those terms and write down the corresponding Feynman rules and do the calculations. And the answer I claimed that time was that this can be written as exponential minus d4q 2 pi 4 1 by 4 g square of q f mu nu tilde of minus q f mu nu bar tilde of q a and a with 1 by g square q given by 1 by g square 0 minus log q square by 48 pi square 1 minus 12 CV plus CRS plus 4 CRF, where trace of TAR, TBR means the SUN representation matrices for a representation small r, could be n-dimensional or a joint representation or any other representation. The trace of this object is C of r delta AV. So that C of r is some number that characterizes the representation. And for n-dimensional representation, C of r, if you remember it, was half. Is that? And for adjoint representation, C of r is CV, and which for SUN gauge theory is capital N. So this C of Rs is now this C corresponding to the representation Rs that the scalar field is it. And this C of R 4 times CRF is the C corresponding to the representation RF that the fermions, Dirac fermions are in. So this is the calculation that I had given as an exercise for you guys. Now tell me who is going to do it on the blackboard. Who are the volunteers? One of you has to do the scalar and one fermions. But let me know who all have attempted it and what were the groups. Let's say first group, scalar part. No, it was not done in groups, it was done separately. Yeah, it doesn't matter, whatever is the formation. So then I'll pick up one person from one group and another person from another group. So these two people, did anybody else discuss with them? Did you discuss it with anybody? The same group. And you? You have not done. What about you? You were with any group or on your own? You have done it. So now tell me, give me two, let's start with scalar fields. Scalar fields are slightly easier. Volunteer. You want to do it? Come. Now others who have not done it, follow it closely, and if there are any questions, ask them. And there is some minus signs problem, we'll try to fix it on the way. Let's see where it is. We'll fix it. Did I write Feynman rules for this last time? I think I did wrote for. So,
We have to sort that out as well.
okay, let's see, start with Feynman rules if you want to start with that. Maybe use the center part. We can keep, this is the answer we want, right?
So this
Do
is
you want to keep the same notation that I had, or you want to use your own notation? Because I had to do that dotted line for scalar field, right?
oh yeah, okay, yeah, that's what I use.
So we kept solid line for a background.
Yeah, that's what I use. And so this is the propagator, and the vertex factor for this diagram is taking all momenta going inwards.
Is that sign problem?
That is a solid, I mean, fact, right?
For scalar field, I put a dotted line.
So these were the Feynman rules in the momentum space.
Is everybody with you?
So
Yeah, there's a minus sign, overall minus sign. Is that what? Is that what you're talking about?
The overall minus sign will get cancelled by this minus sign.
No. The vertex is in the 4-point function, there is an extra minus sign. That is because vertex is from minus s. Maybe I didn't write it that time, but I have it in my notes.
That should be plus plus. As I finally.
Yes.
One
Speaking about
minus
this,
I, one plus I because of one conjugate and another conjugate. So that is fine.
yeah.
But then overall, there is a minus sign because of s minus exponential of minus s.
Yeah, so that still stays. I mean,
Yeah, but that is you could put it in the vertex. Anyway, we'll keep that sign here and let's do calculation. And there's an extra sign in the 4-point now.
Yeah, so,
you understand what I'm saying? Because what you have is exponential minus s.
so
And you
that's
take
what
the
we were
4-point,
speaking about, right? There's an extra minus and an
term
e power
from
minus
there
s.
down there.
So that we
That
keep here or we
minus
don't
s,
keep here?
There's an extra minus sign there. No, in this vertex that's not there.
But that shouldn't change anything, right?
Well, that will not change. Yeah, it will be square of that, right? The graph will have been square. No,
No, sir.
no. That there's one term with that sign.
Right.
One graph will come with that sign. Anyway, keep that sign. If we're good here, let's go.
Okay.
Let's not spend too much time on it.
Okay, so I'll rub this part here,
Yeah,
beta
that will
function.
go. Except perhaps keep the action parts for a while. Oh, you didn't define one rules, fine. So now you can go, yes.
So what we had to find was this pi b mu we now want to identify what this would be by substituting these factors for these particular diagrams. So that would be,
Stop him if you have any question.
so I'll do it for this diagram first. Here A, B, Q plus K and K. So this factor of half comes because when we expand the action in the exponent and we expand it out, so we keep the second order term, and the second order term always comes with a factor of half. It's like e power x is equal to 1 plus x squared by 2. So that too. So this LM here is being contracted with this LM here because these are the only two indices which are there, so they'll have to be contracted with one another. So that's what this, and no, that's just this. I have still not put this factor yet. I'll do that. So this I comes from here, this I comes from there. There will be one more I which will come from the momentum which I am going to write down. This one? Yeah, this is LM.
Order ML.
Okay.
Is that clear to everybody? That's an important thing to realize, that it must come as a trace. Contractions are in such way that it has to be trace of TA and TB.
Yeah. So now, since the way we wrote the Feynman rules here, all moments are going in. So we'll have to take care of some signs here, because here the way this has this I mark the momentum here says that Q plus K is leaving this vertex here. So I have to take care of those signs. So when we do that, we get so this factor comes for my, so there's a okay, wait, I think there's a small mistake here. Yeah, no, this is right. So that is for the first factor. Yeah, this for the first factor, first vertex. Yeah, this is it. This is the.
That's 2K minus 2K plus Q. Write the plus clearly. The first one.
This is minus 2K minus mu, minus Q.
Minus, correct. That's fine.
And 2K plus Q. So when we so now there's a I square here, so that goes off, and this is the trace. So this is nothing but CRS as defined over there with a delta AV. So that is half of CRS delta AP. Yeah, this is the expression for this diagram. Is this right? So for this one, we have okay. We make use of this vertex factor this time because we have two A bar legs and also two scalar field legs. So this has a factor of -I here. So you use that. Oh yeah, D4K. Sorry. 4K, K square. Yeah, this is it. So let me just add these two, and I isolate out these factors here. Yeah, that's right. PM and P. Yeah. If we simplify this, this will give me a again trace. So I'll do that also. So
There's a sign problem in the first.
yeah, there's this extra.
And the sign is because when you wrote the second vertex,
Yeah. This
second
and
vertex,
this. Yeah.
you wrote its coefficient to be I times T.
That's right. This one.
Yes.
Yeah.
It is minus I times T. Because it is conjugate of this vertex. Phi and phi stars are interchangeable.
Yeah, I guess that. So you're saying that this is phi star here, and this is phi star, and this is phi here, phi here.
No, that's the other way. The upper one is phi star.
Yeah. So phi star, phi star.
No, this leg it's phi star and the other leg is phi.
Yeah. I mean, I got
See,
it.
this is phi star, huh? And this is phi and phi star. So this is conjugate of that. So phi star, this is complex conjugate of this vertex.
Okay. But should we not think of this line as being of one particular field phi and
No,
this one?
no, this line is with phi on one, phi star on one side and phi on this. That's what arrow on this line is, right? This arrow. That phi star on this side and phi on this.
Oh yeah.
So is that minus? But now second one, let me see, your second one is there minus sign. No, second one, why is there a minus sign?
There will be a minus sign if we take that extra minus sign from the exponential.
No, second one is I think still okay, right?
Second one,
Nothing.
Have a minus sign. That will be that plus the.
You mean this for this one itself?
yes. Now the first one, there's a minus sign because in the Feynman rule there was an extra minus sign.
By first one,
The
you
4-point function.
this one.
Yes. This 4-point function, because of minus s that you started with, that extra minus in the s gives you an extra minus on this vertex. Which I may not have written it, but I have it in my notes. And that is what will give you the last diagram with the overall minus sign. Is it okay?
So,
This vertex.
so
this
this
vertex-
is fine,
this
right?
vertex has an extra minus sign.
If the vertex has a minus sign, extra minus sign, then this will have an extra.
Okay.
This vertex has an extra minus. That comes from this minus.
But when we write down the rules, we always know that this minus sign is always there. We have it in the back of
no,
our mind.
No, no, you must always keep this minus sign in your vertices.
Okay.
In the propagator, you don't worry, keep it, because in propagator, it is with this minus sign that inverse of the quadratic part from here gives you the propagator. But in vertices, this minus sign you have to take into account. Here you may have done the same minus sign error, but here it comes in the diagram as a square, it doesn't matter.
Okay.
But in this one, it will matter.
So there is actually a minus sign here also, an
There may
extra
be a
minus
sign
sign.
also, but I think, I don't think careful about that. But that, it will always come in conjugated way, so square of that in diagrams. So that will not be relevant. But this one is relevant.
Yes.
Is that okay? Huh?
This one is just overall minus sign is.
So in the first term you still won't change a sign, right? Since there's a there'll be a minus sign for
So quadratic, so that minus sign will go.
yeah for the k factor there'll be a minus sign, and for the t factor also there'll be a minus sign.
And there's a.
No, now it's okay, right? So there's a minus sign extra which comes in here, but there won't be a minus sign which will show up here, because if you are going to the minus sign for this and this are going to cancel out. So
Have an extra minus sign, conjugate, right? Still it comes in there.
No, in the first diagram.
But that.
First diagram, the minus sign is irrelevant because it will come in squares, conjugated ones, right?
So in the.
But the second diagram, it's relevant.
But in the final answer,
Yes.
there will be a problem. You were saying this. Here there will be a minus sign because we are conjugating the vertex.
No. The corresponding, the vertex here, that you have here. You have here, so that in a part. What you have here, this.
so okay, this won't pick up any sign here.
This is as it is all right, except that this should have been here. You should have written like this.
No, I was wondering about this I which comes in front of the k factors. This I.
That you have done all right because you have done this calculation here carefully.
Okay. So
That
they'll
is as it is because you labeled upper line with exponential ik1 and lower line with see by doing Fourier transform. So if you kept track of those objects clearly because those are the same factors. Because those are associated with the Fourier transforms of this line and this line.
yeah.
So those you have kept track of it. So that calculation is all right. But this should have been this.
So there'll be an extra minus sign here, and also there'll be an extra minus sign here.
So this is
No, sir, you have already. Okay, yeah.
now that is coming out in the right combination you want. And this is the combination it must be because the combination. So write down the final answer.
The indices should be
With the dagger, I think this is not the right one.
The indices are of the full dagger.
Yes. This is R with the full dagger, and that is when they have the right dagger. Because in one vertex, the line that is 5 star, on the second vertex, that line is 5.
R is with the trace of TA, R is TB, R is dagger.
D dagger is T.
Okay,
Because we are taking self joint IT.
as the previous one.
By rotation you won't get it, but by mirror image you will get it. That's what that is. Because they have
K1, K2 are the same.
even at K2 are fixed labels. Is this correct?
You can write it as a 1/4 2 with the delta meter. Put it in there. Pi mu.
This is how it was in the
Mm-hmm.
so put
Simplify the same.
signs.
You mean just change this sign here?
change this sign and
Okay.
this sign here. But why is the half here? Well, it's half.
Because I have I have pulled out a factor of 2 also in this definition here. So
So what pi mu complete counts. Oh, you call this pi.
So
You call pi mu. Is that how it was earlier? It's the same pi mu that we had earlier. Is it the same?
yeah, I guess yeah, isn't it the same?
And that one also had a half here?
No, that had a 1/4, but that 2 delta. You know the 1/4 option.
2 delta mu.
Okay, that's the same. All right. Yes. This is plus. Okay. So that's what it is.
And then, if you